This is lecture number 8 of the course Engineering Mechanics. Lecture 8. In this lecture, I am going to first solve this example problem. In this problem, we have an assembly of several rigid bodies. If I identify these rigid bodies, then this is what I call as rigid body 1. In the background, indeed, there is this ground frame also, which can be considered to be a rigid body on its own. However, the way this problem is presented, RB1 can easily be considered as an extension, as a part of RB1, as a part of the ground frame itself. Because RB1, what I marked here, this shaft is not performing any motion with respect to the ground, and thus it is legitimate to call both this blue marked body as well as the ground frame as RB1. Then I have the second rigid body which is attached to RB1. This is I call as RB2, rigid body 2. Then we have the next adjacent rigid body, which I am now outlining with green color. And we will call this as RB3. Then next to RB3, we have a straight rod, which I am outlining now with this purple color. Let's call it RB4. It is given in the problem statement that this thin rod, which I called as RB4, it moves at a constant speed of 0.1 meter per second out of the tube BC. So if we follow our notation, this particular information can be expressed in mathematical terms as VA3. This is point A here. Point A is the tip of RB4. So VA3 is given to be 0.1 meters per second, and its direction is at this current instant along the j hat unit vector. So j hat is this direction, I hat is along x, and we will mark the direction along the z axis as the k unit vector. This is a given information. Further, it is mentioned here that the thin rod moves with a constant speed. that word constant tells me that AA3 will be null vector. It is 0. Moving on, at the same time, tube BC rotates at the constant rate of 2 radians per second with respect to arm CD. So tube BC is what I am calling as RB3, and tube CD, arm CD is what I am calling as RB2. So the second statement in the second text statement is telling me that omega of 3 with respect to 4 is not 4 but omega of 3 with respect to body 2 is 2 radians per second, and the direction of this vector has to be inferred from this arrow that is shown, the curled arrow that is shown here on the figure itself. So the direction must be along k hat. Further, it is also mentioned that the tube BC rotates at a constant rate. What is the importance of this constant rate? So this vector omega 32, since it is a vector, there are two ways in which this vector can change. Either the magnitude changes or its direction changes. In either case, omega 32 will change. The change of omega 32 can we use the given information about the change in omega 32 and translate it into a mathematical expression here. The quantity of interest here is omega dot 32. Now note that omega dot 32 is the angular acceleration of RB3 with respect to RB2. Now given the problem, omega dot 32, the vector, that will have zero magnitude because somebody, an observer who is sitting on RB2, he sees the motion, the angular velocity of RB3 as always pointing in this direction. So for this observer, the vector omega 32 is never changing its direction. It is always pointing along k hat. And for this observer, the magnitude of omega 32 also remains constant because it is mentioned here. And thus, our conclusion is that omega dot 32 must be a zero vector, a null vector. Moving on further, the problem statement says that knowing that the entire assembly, I would like to use a different phrase here. What they actually mean is knowing that RB2 or arm CD rotates about the x-axis at a constant rate of 1 radian per second. They want us to find something. I'll stop here, take a pause here, and try to translate this information. The information given in the statement means omega 2 1 is 1 radians per second and it is directed along I. But again, for an observer who is tied to RB1, does he see any change in omega to 1? So my question is, can we infer something about omega to 1? So for this observer here, the vector omega to 1 is having a constant magnitude which is 1 radian per second, and for this observer the direction of omega to 1 is always along I hat, is always along this rod itself or the RB1 itself. The direction is always along RB1 itself, and thus my conclusion is that this is also 0. So we have a set of 6 expressions that I have written at the bottom of the slide, and all this is coming from the statement of the problem available to us. Now, using this information, we are being asked now to find the velocity and acceleration of point A with respect to ground. So we have an assembly of rigid bodies. Our observer is fixed to ground and he wants to know the velocity and acceleration of this point. As seen by this man, the velocity and acceleration of A is not straightforward. Indeed, the motion that A executes, as seen by this observer, is a complicated three-dimensional motion. To find velocity of A with respect to RB1, which is same as 1 is same as ground, and acceleration of A with respect to 1 seems complicated if we try to visualize the motion of A directly through the eyes of this observer here. And this is where the relationships, the two relationships that we derived in the previous class are going to be helpful. What are those relationships? The first relationship is the velocity transfer relationship, and the other relationship is the acceleration transfer relationship. I would like to remind ourselves that both these relationships invoke the concept of an intermediate frame and an intermediate point. To write the expression of a point using a frame, an intermediate frame, from where the motion of A appears to be simpler and more straightforward. And this very fact will allow us to Finally, find VA1 and AA1. So let's proceed with the solution steps. How do we find VA1 and AA1? All right. So to find VA1, I am going to use IF, which is the short form of intermediate frame, as RB3. What guides my choice? I choose a frame to be an intermediate frame to find this quantity, because if an observer is sitting on RB3, the velocity of A, the motion of A rather, becomes very straightforward. For an observer sitting on RB3, it is very easy to visualize that the motion of A is nothing but along a straight line, as seen by this man. That decides my choice of IF. So you should choose the IF to be a frame from where the motion of the particle of interest is either known or it is very straightforward or very simple to express. Once I have chosen an IF, I also need an IP. Intermediate point, and I am going to choose the intermediate point to be point C, which is right here. What governs or what guides me while choosing an IP? The intermediate point should be chosen such that typically it lies at the interface of your IF and the next adjacent frame. So this is RB3 is my IF and the next adjacent frame is RB2. So I would choose my point C to be somewhere on the interface of these two RBs or these two frames. So once I make this choice of RB3, once I make this choice of IF and IP, I can write VA1 using velocity transfer relationship as three. Having written this expression, let's now sweep this equation from right to left and list what are the known quantities and what the unknown quantities are. If a quantity is known, we are ready to do calculations. There is nothing more to be done as far as formulation is concerned. But if there is an unknown I come across, I will have to do some extra formulations. I am prepared to do that. So let's start with the rightmost term, VA3. Is VA3 a known quantity or an unknown? It is a known quantity. I put K. K stands for known. If you go to the previous slide, you would see that VA3 is a known quantity based on the given information. It is actually U times along j hat. Then I move to the next quantity, RAC. Is RAC a known quantity? RAC, we look at the geometry, the details, geometric details given. Yes, RAC is a known quantity. At this particular instant, it is 0.3 times J. So this is also a known quantity. Next we move to omega 31. Is omega 31 a known quantity? Omega 31 is the angular velocity of RB3 as seen by frame, an observer who is tied to frame 1. If you go back to the previous slide, you will realize that omega 31 is not a given information. So it is an unknown quantity right now. I will have to do some extra formulation to get this. What is that formulation? Recall from our previous lectures that we derived an expression for a composition of reference frames. We had an expression which allowed us to write the angular velocity of frame 3 with respect to frame 1 as omega of 3 with respect to 2 and then omega of 2 with respect to 1. Going back to the previous slide, you would notice that indeed this quantity is known, omega 32 is given, and also omega 21 is given. So which in turn makes omega 31 as known quantity. So earlier it was unknown, now I strike off u and I write k above omega 31. So that quantity is also known. The next quantity is Vc1. What is Vc1? To get Vc1, I will once again use the velocity transfer relationship. However, this time I will try to find Vc1 using a different intermediate frame and a different intermediate point. What will be that intermediate point and what will be that intermediate frame? These choices will be governed by the two guidelines that I mentioned while I was trying to explain the choices of IF and IP for VA1. My guideline about the choice of IF was, I repeat, IF should be a frame from where the motion of the point of interest, which in this case is point C, is known or is very straightforward to visualize. Based on this guideline, I choose the IF to be RB2. Indeed, for a human observer who is tied to RB2, the point C is not moving at all. So in that way, velocity of point C with respect to RB2 is known, and that's why I am choosing IF to be RB2. Then comes the question, what should be the IP? Again, I go back to the guideline I mentioned earlier in context of VA1. The guideline was that you should choose IP to be a point such that it lies on the interface of your IF and the next adjacent rigid body. So in this case, the IF is already chosen to be RB2 and then the next rigid body is RB1. So I would choose point D to be my IP. Once I make that choice, then I can write Vc1 using the velocity transfer relationship as one is VD1, okay, 2, 1, C2. Having written this relationship, I would like to again sweep from right to left and see what the known quantities are and what the unknown quantities are. This quantity Vc2 is known. In fact, this is equal to 0 because C is a point fixed into itself. RCD is a geometric quantity. Is it given? Indeed it is given. RCD is 0.5 meters in k hat direction. So this quantity is also known. K is supposed to represent a known quantity, U is supposed to represent an unknown quantity. Is omega 21 known? Indeed it is known. If you go to the first slide, we did extract this information from the given problem statement itself. Is VD1 a known quantity? You observe VD1, you observe the point D here. It is not moving at all. It is a known quantity because D is a point fixed in 1 also. D is a point fixed in 1 also. So once you have swept the right hand side of this expression from right to left, we are in a position to say that Vc1 itself is a known quantity. Now if Vc1 is a known quantity, I am going back to, let me call this equation 1 and let me call this equation 2. So once we have found Vc1 in 2, we take it, we go to equation 1 and mark this also as a known quantity, and then you realize that the entire right hand side of equation 1 is known. It implies that Va1 is also known. If you use the numerical values given in the problem statement, the answer that we must get is going to mention the final answer here. It is this is the final answer. So the first part of the problem we have solved. Now let's move to the next part. The next part is to find acceleration of A with respect to frame 1. We need to find AA1. Again, to find AA1, we will use velocity transfer, we will use the acceleration transfer relationship as many times as it is required. And every time we try to use the acceleration transfer relationship, we will have to make appropriate choices of the intermediate frame and a corresponding intermediate point. It turns out for problems of this type, wherein you have to find both velocity and acceleration of the same point with respect to the same reference frame or the same ground frame, the choices of IF and IP that we have already made for the velocity calculation will remain the same for the acceleration calculation as well. So my first choice of IF, like last time, is going to be RB3, and my IP is going to be chosen as point C. Accordingly, I can express AA1 as alright. Like last time, what I did for the velocity transfer relationship, I will start sweeping from right to left and mark the known quantities as K and the unknown quantities as U. I start with AA3. Is AA3 known? Indeed, AA3 is known from the problem statement itself. If you go to the first slide that I showed, we convinced ourselves that AA3 is indeed 0. So I will mark this quantity as known. VA3 is also a known quantity coming directly from the problem statement, and that is U times J. Is omega 31 known? Yes, omega 31 is known. I calculated it on my previous slide while I was using the velocity transfer relationship. So this is also a known quantity. Is RAC known? Yes, previous slide. Omega 31, repeated incidences of the same quantity, RAC known. Now we get stuck at omega dot 31. Is omega 31 known or unknown? If you go to the very first slide of the lecture, you would not see any information about omega dot 31, angular acceleration of 3 with respect to 1. However, we can find this. Now we can find this. How do we find this? Omega dot 31 can be written as omega dot 32 This is a relationship that we derived 2 classes ago for a set of 3 reference frames. This can be used here. Sweeping from right to left, is omega 32 known? Yes, known from the problem statement. Omega 21 is also known from the problem statement. Omega dot 21 is also known. In fact, this is 0. And omega dot 32 is also known, and that is also equal to 0 from the problem statement itself. Consequently, I can now say that I know omega dot 31, so I will strike off U and write here known. So far, we have been able to find all the quantities coming from the right hand side of equation number 3. Now we come to AC1. Is AC1 known? It's not known currently, but then I can find AC1, and to find AC1 I am going to invoke the acceleration transfer relationship again, with my IF being 2 and IP being D. Again, these are the same choices of IF and IP that I used when I was trying to find VC1, velocity of C with respect to 1. Same choices. If I make these choices, AC1 is expressed as have to be careful with these indices. This is AC2. I want to review it once more after writing to ensure I have not made any mistakes. AC1 is AD1 I believe it is correct. I sweep from the right to left and mark things as K or U. AC2 is known. In fact, it is 0 because C is fixed in 2. VC2 is also known. It is equal to 0 because C is fixed in 2. Same reason. Omega 21 is a known quantity coming directly from the problem statement. RCD is also known based on the given geometric information. Omega 21 repeated indices known quantity. RCD is known quantity. Omega dot 21 is also known. It is actually 0 given. And then finally we come to AD1, and you realize that D is a fixed point in 1 also, and that's why this is also known. It is equal to 0 because D is a point fixed in 1. So my conclusion is that everything on the right hand side of equation number 4 is not now known, which means AC1 is known, and I will go back here and strike off U and write AC1 as known. Now if you observe equation number 3, everything on the right hand side is known, so eventually you will be able to find AA1. AA1 is not now a known quantity. And I would like to write the final answer so that viewers can verify their own calculations. According to my calculations, this is what the vector is. And the units meters per second square. That completes the solution of this problem. We were asked to find velocity and acceleration of the end of the rod with respect to ground, and we have completed it.